Today we're going to continue our exploration of data using tables and graphs by talking about a type of graph. Specifically, we're going to talk about histograms. Now, frequency distributions are super useful for summarizing data and investigating what the distribution looks like, but they require us to look at numbers along the way or percentages, and they don't really give us just like an overall visual image that we can glance at and know something immediately without having to dig a little bit. Histograms give us just that. A histogram is a graph that makes it easier for us to interpret those tables of numbers that we get with our frequency distribution. So a histogram is a graph consisting of bars of equal width that are drawn adjacent to each other unless there's some gap in the data. This is not to be confused with a bar graph. So a bar graph, you leave spaces between the data because it doesn't make sense to have the bars touching each other necessarily. In a histogram, it makes sense for those bars to touch each other because they have a shared boundary. The horizontal scale on our histogram is going to represent the classes of quantitative data values, those same classes that we use in our frequency distribution. And the vertical scale is going to represent the frequencies that are in our frequency distribution. So the heights of the bars are going to correspond to the frequency values in that frequency distribution for the class. So let's talk about some uses of them. First, they visually display the shape of the distribution of the data. This is something that the frequency distribution tells us, but we have to understand the numbers and look at the numbers in comparison to one another in order to do that. Histograms do that comparison for us and give us a straightforward visual to look at. They also show us the location of the center of the data. With just a glance, we can ballpark eyeball where the center of the data is and look on the horizontal axis to determine what that value is. They also show us the spread of the data. They show us where it starts and where it ends, and how spaced out it is, how clumped towards the center it is. And we can, again, read these values right off of the horizontal axis. And finally, it identifies outliers. If we have outliers, there will be gaps between most of our data and that outlier value. So here's an example of a frequency distribution, like this time at McDonald's for lunch in seconds that we used in our frequency distribution discussion. And here's the histogram that goes with it. By looking at the histogram, we immediately know what the most likely timing we would have, and we can see that it's twice as likely pretty easily just glancing at it, that it's twice as tall, so it's twice as likely as the other outcomes. A relative frequency histogram is the same as a regular histogram. The horizontal scale stays the same. It's still our class boundaries. But on the vertical scale, instead of having those frequency values, it has percentage values to give the relative frequencies. The shape and the spread and everything about the histogram will stay the same from the frequency histogram, the regular histogram, to the relative frequency histogram. The only thing that changes is the labels on the vertical axis. So there's some things that we can look at when we're thinking about interpreting histograms. The first is the center of the data. We want to know where the center of the data is. The histogram lets us look and eyeball where that value is. We also want to know something about the variation. The variation is the spread of the data. How spread out is it? How condensed is it? What's the range? That type of stuff. All right. The shape of the distribution overall. We'll talk a little bit more about some common shapes in a minute. And then whether there are any outliers Again, this is the values that fall like there's a gap between the rest of the data and these values. They're very easy to spot this way. And time. Time is not always actually relevant, as are outliers. There's not always outliers, and time, like the idea of the data changing over time, we don't necessarily see that depending on what our histogram is showing us. So to remember these 5 things, you can remember CV dot, or you can remember them, whatever works best for you. All right. So let's talk about some shapes of histograms. These are 4 of our most common distribution shapes, all summarized in one place. We have normal distributions, uniform distributions, or our distribution can be skewed left or skewed right. We're going to talk about what each of these mean now. So a normal distribution, this is a distribution that has more or less the shape of a bell. You see the red bell drawn into this. All right. Does it have to be perfect? No. All right. But it's more or less that bell shape. So this is an example of a histogram that's roughly bell-shaped, so we would say the data has a normal distribution, or an approximately normal distribution. Skewness. If something's not normal, one of the things that could happen is it could be skewed. So if it's not symmetric, it tends to extend out one way or the other, then it's skewed. When our data is skewed to the right, or towards the positive values, has a longer tail out towards the positive values, towards the right, we say it's skewed to the right. A way to remember this is if you think about your toes as each being the bar of a histogram and you look at your left and your right foot, your right foot is the shape of a histogram that is skewed to the right. So you can see that here where the bulk of our data is up towards the left, but then it kind of skews out and it goes towards the right. Similarly, we can go the other way and we can have it be skewed to the left, or negatively skewed. So it's skewed towards the negative values. So there's more values hanging out in this tail to the left. So it looks like everything's bulked up on the right side and it's just trailing off to the left. And again, if you think about your toes as the bars of a histogram, your left foot has the shape of a histogram that is skewed to the left. So we're going to talk just a little bit about assessing normality with normal quantile plots here. You do not need to know how to make a normal quantile plot right now. What you do need to know is how to deal with one if you're given one. All right. So if something is a normal distribution, when you see the normal quantile plot for it, the pattern of the points in that plot is going to be reasonably close to a straight line, and there's not going to be any pattern that you see that you can go, there's a pattern that is not a straight line. All right. If it's not normal, then the points are not going to lie on a straight line, or there's going to be some kind of pattern that you're going to say, you know, that straight line fits decently, but there's a pattern that's not that straight line. So let's take a look at a few examples real quick. So here's an example of a normal distribution. Do the points fall exactly on this line? No, they don't, right? But there's not really a pattern to the way that they don't fall on this line. When I look at that, I don't immediately see something that's not a straight line. And so this is a normal distribution. This is not a normal distribution. You can see that a lot of the dots don't lie on this straight line, and you can kind of see that they go up and over. We've got kind of like a square root or some kind of exponential type shape going on with the dots there. All right. So if the points don't lie close to a straight line, like they don't here, then this is not a normal distribution. Here's an example of something that's not a normal distribution, but they lie really close to that straight line. But if we look at them, we see kind of a really nice shape that curves around and is not actually a straight line pattern. So this is also a not normal distribution, or not a normal distribution. Even though they lie close to that straight line, there's a definite pattern that is not a straight line. Again, you don't need to be able to make these normal quantile plots, but if you're given one, you should be able to discern whether a distribution is normal or not.